and thanks for watching Edupedia World Videos. We've seen many problems and their solutions to the Schrodinger equation in one dimension, such as the harmonic oscillator, the infinite square well, and even the finite square well, but now we are going to move on to a more realistic case, the Schrodinger equation in 3 dimensions. So let's start with the very first equation we saw in this lecture series, the Schrodinger equation, not the time independent version one, but the original Schrodinger equation that was written as this: iota h del psi by del t, and this is the capital Psi which depends on both time and position, is equal to minus h square by 2m del squared psi by del x squared plus v of psi. Now what happens to this in 3 dimensions? We get 2 more terms here. Instead of just del squared psi by del x squared, we get this plus del squared psi by del y squared plus del squared psi by del z squared. And the other differences are v, instead of being dependent on x, now is dependent on x, y and z, and capital Psi also, instead of being dependent on x and t, it is now dependent on x, y, z and t. And the rigorous derivation of this equation is such as, we can write this as is equal to h psi, where h is the Hamiltonian, which is the operator for energy, that is equal to v plus p squared by 2m, where p squared by 2m can obviously be written as px squared by 2m plus py squared by 2m plus pz squared by 2m. And the substitutions in this case are, originally we had px is equal to h by iota del by del x. Similarly, you have py, the momentum operator in the y direction, is equal to h by iota del by del y, and pz is equal to h by iota del by del z. And so you, for example, take py squared by 2m, that gives us minus h squared by 2m del squared psi by del y squared. This equation can better be written using the Laplacian operator, which is basically, we can write it as iota h del psi by del t is equal to minus h square by 2m del squared psi plus v psi. Now what is this del squared? It is the Laplacian operator and its value in the Cartesian coordinates. Remember, 3-dimensional coordinates can be of many types: spherical, polar, Cartesian. Right now we are doing with the Cartesian coordinates, which is x, y and z. So in the Cartesian coordinates, the Laplacian looks like this: del squared by del x squared plus del squared by del y squared plus del squared by del c squared. The double partial derivative with respect to x plus the double partial derivative with respect to y plus the double partial derivative with respect to z. There are a couple of other small changes as well from the 1-dimensional case to the 3-dimensional case. Earlier we saw that the probability of finding a particle between x and x plus dx was integral mod psi squared dx, and the integral is between the two values. So now the probability of finding the particle in a volume which is not between x and x plus dx, but between x and x plus dx, y and y plus dy, z and z plus dz, or the 3-dimensional infinitesimal element d cube r, which is dx, dy, dz. So dx is replaced by this, and psi obviously, instead of being dependent on x and t, is dependent on x, y, z and t. So the normalization equation becomes integral mod psi squared. Instead of dx, we get d cube r is equal to 1, where d cube r is the product of the 3 terms dx, dy and dz. Of course, we can do the same thing we did in the very first video and separate it into the time independent case by assuming that psi is dependent on two functions, one only a function of position xyz and the other only a function of momentum, and then you can do this yourself. The final equation we'll get is a complete set of stationary states psi n r t. When I say it depends on r, it basically means it depends on x, y and z in the Cartesian case. This comes out to be equal to some normal psi n r, and this is our goal will be to find out this now, because remember from the normal Schrodinger equation we went on to the time independent Schrodinger equation. So this would be the solution, and we would attach a time dependent and energy dependent factor which would be e to the power minus iota En t by h, where En is the energy in the nth stationary state, the psi n of r is the position wave function. So let's look at what the time independent Schrodinger equation would look like. Once again, the only difference is from instead of d squared by dx squared, we get the Laplacian, and it's still h psi is equal to e psi, but h psi just becomes minus h square by 2m del squared psi by del x squared plus del squared psi by del y squared plus del squared psi by del z squared. And now this is not capital psi, this is only dependent on the position. This is equal to e psi, and that can also be written as minus h squared by 2m del squared. Of course, there is plus v psi as well. And the other difference obviously I talked about was that V, instead of only being dependent on X, a one-dimensional potential, and the whole problem being one-dimensional, V now depends on X, Y and Z. And the final complete set of solutions, which will be a linear combination of the stationary states, will be psi of r and t. This is what we need to find out. This is capital psi. This will be a linear combination. So summation over n Cn times the nth stationary state, psi n of r e to the power minus iota En t by h. And obviously any complicated solution can be written as a linear combination of these stationary states. I won't go into the detail of what stationary states are again, but these are states of definite energy where if you measure the value of energy, you will with 100% probability get the value En. So this was all in the Cartesian coordinates, but goal in the next video is to study the hydrogen atom. And when you study potentials such as the hydrogen atom, which is a Coulomb potential, or any other potentials in 3 dimensions, when you have a central force, a central object at the origin applying the force, it is often better to use spherical coordinates, because very often the potential in spherical coordinates, which are x, y, z, goes to r, theta and phi, it only depends on r. It doesn't depend on theta and phi. This is a very common case, and it makes the mathematics a little simpler. So we'll study the equation in the spherical coordinates for only v depending on r, because we'll see in the next video that in the hydrogen atom v indeed does only depend on r. In fact, you already know the Coulomb potential, and it only depends on the distance between the two objects. So if one of them is at the origin, it only depends on r, not on the angle theta and phi. So this is our next step, to study the Schrodinger equation in spherical coordinates. So before that, we'll just take a little bit of a detour and look into what spherical coordinates are. So this is a diagram of the relationship between Cartesian and spherical coordinates. Cartesian coordinates, as we all know, are x, y and z, 3 mutually perpendicular axes. In the spherical coordinates, we have 3 new variables, r, theta and phi. R is the distance of the point from the origin. So the value of r in terms of x, y and z is root of x squared plus y squared plus z squared. And theta is the angle which this r vector makes with the z axis. So cos theta will be z by r, which is basically z by root of x squared plus y squared plus z squared. And then this is the angle with the z axis. R cos theta is the component along the z axis. R sin theta is the component in the xy plane. So r sin theta itself has 2 components. This line is r sin theta, and it has a cos phi component. r sine theta cos phi, which is the value of x, and it has a sine phi component, which is r sine theta sine phi, which is the value of y. And from these two, you can see the inverse relationship as well. Tan phi is equal to y by x. So I'll repeat this once because this is important, and we'll be using spherical coordinates many times even in other courses. So x, y and z are the distances of the point from three mutually perpendicular axes, the x-axis, y-axis and z-axis. This is the Cartesian coordinate system. In the spherical coordinate system, the first variable is the distance from the origin, root of x squared plus y squared plus z squared. The second variable is the angle which r makes with the z-axis, and in terms of Cartesian coordinates, that is z by r or z by root of x squared plus y squared plus z squared. And then you have r sine theta, which is the projection of r in the xy plane, this line, and it has two components, a cos phi component which is in the x direction and a sine phi component which is in the y direction. There are also differences in the unit vectors. You can have r hat in terms of x hat, y hat, z hat and so on, and also differences in the area element and volume element. For example, the area element in an xy plane would be dx dy in 2 dimensions in Cartesian coordinates, but in polar coordinates it will be something else. Similarly, the volume element in Cartesian coordinates is simply dx dy dz. That's why we saw in a previous video d cube r was equal to dx dy dz. But in the polar coordinates or spherical coordinates, we have a different volume element which we can see here. So this is the original figure r, theta and phi in terms of x, y and z. What we did originally was x went from x to x plus dx. So x was increased by dx, y was increased by dy, z was increased by dz. And we calculated the volume of the new element, which came out to be, because everything is rectangular, dx dy dz. In this case, we take a point at r, theta and phi and we change r by a small amount dr. So it goes outwards by a small distance dr. Then theta becomes theta plus d theta. Theta is increased by d theta and phi is increased by d phi. So once again, we get three sides making the volume element. One of them is simply dr. That is because r goes from r to r plus dr. Then you have theta going from theta to theta plus d theta. So this element will be r d theta, right? Just like the element of a circle is r d theta. And the element in this case, the projection here would be r sine theta. So the element in this case would be r sine theta d phi. So instead of dx, dy and dz, what we have is dr, r d theta and r sine theta d phi, which basically gives us the volume element r squared sine theta d theta d phi dr. And another big difference is the limits. When you, for example, calculating around a sphere, theta will go from 0 to 180 degree, phi will go from 0 to 360 degree, or theta will go from 0 to pi, phi will go from 0 to 2 pi. And that's how you can determine the volume elements. Also, other vectors such as the Laplacian have a different value in spherical coordinates. Now, the mathematics, it ends up being a little bit complicated at this juncture. So we'll only look at the main details. We'll not go into the complete derivation. So first, let's look at what the Laplacian looks like in spherical coordinates. Laplacian in Cartesian coordinates was by del x squared plus del squared by del y squared plus del squared by del z squared. But in polar coordinates or spherical coordinates, it is slightly more complicated, and I'll just write down the value. You can look at the derivation in a textbook, or you don't really need to know the derivation also, and it's somewhat complicated, so we'll just write the main formulas and then go to the solutions. So the Laplacian in spherical coordinates is written as 1 by r square. It has to be in terms of r, theta and phi. Del by del r square del by del r, plus 1 by r square sine theta del by del theta of sine theta del by del theta plus 1 by r squared sine square theta del squared by del phi squared. So we have a term in which you have the double derivative of r, you have the double derivative of theta and the double derivative of phi, but there are some other terms as well. And so we know what the Schrodinger equation looks like. minus h square by 2m, and in 3 dimensions it is del squared psi plus v psi is equal to e psi. Now what we'll do is we'll separate this once again the same way we did for the original equation, separating it into position and time. Now what we'll do is we'll assume that v only depends on r, and we'll separate the solution into radial and angular parts. So basically what we'll assume is capital psi, this is all capital psi, of r, theta and phi is equal to some capital R function of r multiplied by some capital theta function of theta and some capital phi function of phi. So what we'll do is we'll do separation of variables and try to find solutions which depend as the product of three solutions, r, theta, theta and phi, phi, just like we did when we separated the position and time in the previous case. And once again, I'll not go into the detailed mathematics, but we'll get two separate solutions. Here, generally what we do is these two combined, we take it to be the angular part y, theta and phi. So sometimes it will be written as r times y, theta and phi, where this is the radial part and this is the angular part, but this is also the product of two other functions. When we do separation of variables, you can do it yourself or look at it in a textbook. We'll once again reach the point which we've reached many times before, where we'll have two sides of an equation equal to a constant. One side will depend only on r and the other side will depend only on theta and phi. And so we'll use separation of variables, and for reasons that will become understandable to you later on, it will be convenient to take both sides equal to L times L plus 1. Normally we take it to be equal to L or some constant, but the equation becomes much simpler if we take it to be a constant whose value is L into L plus 1, just to make the mathematics a little bit simpler. So I'll write down the final two equations which we are left with. One equation is for the radial part and the other equation is for the angular part. So the radial part tells us 1 by r, and this r is dependent on small r, d by dr. Now we don't need del. Now it's just a function of r, so we only need d by dr, r squared dr by dr minus 2m r squared by h squared v of r minus e. This is equal to L into L plus 1. This is the radial equation. And then we have the angular equation 1 by y. Y depends on theta and phi, remember. 1 by sine theta del by del theta. And now we're using del because y depends on both theta and phi. Del theta sine theta del y by del theta plus 1 by sine square theta del 2y by del phi squared. And this is equal to minus L into L plus 1. This is the angular equation. And here we see something interesting. The potential only occurs in the linear equation as long as it is only dependent on r, which we've assumed. So as long as the potential only depends on r, the potential only determines r of r. Y of theta and phi is basically determined completely by the angular equation, and we do not even need to know v of r to solve it. So we'll go one step further now and solve the angular equation. We can't obviously solve the linear equation until we know what v of r is, and that will be something for the next video, where we'll assume v of r is the Coulomb potential and try to find out the energy levels for the hydrogen atom. But for now, we'll just solve this equation because this equation does not tell us that we need to know v of r, and this equation is the angular equation. And once again, we'll assume separation of variables. We'll simply write y of theta and phi as a product of two functions, one only dependent on theta and one only dependent on phi. And I won't go once again into the details, but we'll put this inside this equation, and we'll get once again two separate LHS and RHS, one depending only on theta, the other depending only on phi. So both of them will have to be equal to a constant, and just like we took the constant to be L into L plus 1, here we'll take the constant to be m squared. Once again, this is because somebody has previously done by taking it A and B, and we discovered that this is what makes it mathematically convenient. So I'll write down once again, in terms of the angular equation, what the theta equation and the phi equation is. You can do it yourself. The mathematics does turn out to be a little bit complicated. So 1 by theta, this is the theta equation. Sine theta d by d theta of sine theta d capital theta by d theta plus L into L plus 1 sine square theta. This is the bracket is here. This is equal to m squared, and the phi equation is 1 by phi d squared phi by d phi squared is equal to minus m squared. So this is the equation which only contains theta values, the variable theta, and this is the equation which only contains the value phi, and this is an easy equation whose solution you can see directly. Now remember what we are doing here. We are solving for a potential that only depends on r. So for a potential that only depends on r, the angular part of the wave function is already determined. We don't even need to know what the r dependence of potential is. And this equation you can solve yourself. It has a very simple solution, which is phi of phi is equal to e to the power iota m phi. But there's another constraint here, which is that phi keeps going around in values of 2 pi. So whenever you have phi, you should have phi of phi plus 2 pi is equal to phi of phi, because if you increase the angle by 2 pi, the value itself remains the same. So this tells us that m should be an integer, because if m is an integer, then once you increase it by 2 pi, you'll get e to the power 2 pi iota, which is 1. So m is equal to 0, plus minus 1, plus minus 2, and so on. So we've seen a remarkable thing. We've already determined a third of the wave function phi of phi, and its value is equal to e to the power iota m phi, where m is an integer. The solution to this equation, the equation of theta, turns out to be a little bit more complicated. I'll just write it down. I won't go into the details. And it is theta of theta is equal to a, where a is just the normalization constant. We haven't used the normalization constant yet. Now we'll see that we'll just use the normalization constant in theta of theta, and we won't use it in r and phi because they will automatically be normalized then. So a into PLM of cos theta, where PLM is what is called an associated Legendre function. I'll just write down how to calculate the values of this. You won't need to get into the details of it. PLM of anything x is equal to 1 minus x squared to the power of mod m by 2 d by dx to the power of mod m PL of x. PL of x is a Legendre polynomial, and it is defined by PL of x is equal to 1 by 2 to the power L factorial d by dx to the power L x squared minus 1 to the power L. So this is basically for any value of L, you can get the value of PL of x. You can put this here for the value of m, you can get PLM of x, and PLM of cos theta is a solution to this. But there's another constraint which we can see from this equation, d by dx to the power of L, which means L has to be an integer. So just like m, L has to be an integer. But there is one more thing we see. PL of x is generally, if you try to calculate it, a polynomial of degree L. And if we take the mth derivative of PL of x, if mod m is greater than L, this turns out to be 0. This is like the third derivative of a quadratic equation, which will be 0. So not only is L an integer, but mod m has to be less than equal to L. What this tells us is m is equal to 0 plus minus 1 plus minus 2 dot 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 till plus minus L, which is a total of 2L plus 1 values. So for example, if the value of L is 4, then M can have 4 into 2, 8 plus 1, 9 possible values, which is minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and 4. Right, and you've already probably seen these types of values before. This comes out in the hydrogen atom, where L is called the azimuthal quantum number and M is called the magnetic quantum number. We haven't yet gone into the hydrogen atom because for that we'll have to put the Coulomb potential, but this is a result which is true for any potential that depends only on R. We've already seen what the values are. Theta of theta is equal to A times P L M of cos theta, phi of phi is equal to e to the power iota m phi, where both L and M are integers and mod M is less than or equal to L. So M has these values, which are a total of 2L plus 1 values for each value of L. L could be 7, then M will have 15 values. For every value of L, M has 2L plus 1 possible values. Now this is really as far as we can go without knowing what V of R is. The next step is to try to solve the radial equation, where we'll assume V of R is the Coulomb potential, and now we get into the real meat and bones of quantum mechanics. We are trying to find how the wave function behaves, how the electron behaves under the influence of a single proton, which is basically the hydrogen atom. So that's the topic for the next video. Thank you.